Thank you. How many of you remember interacting with Dragon speech software, dictation software? Okay. I interacted with it in early 2000s, and that was my inspiration to work in voice AI, because when I interacted with it, it didn't work for me at all. It didn't understand my Indian accent, and I was like, okay, after I graduate from school, I'm going to go work in voice AI. So today I'm going to talk about how voice AI has matured, and voice AI is ready for enterprise, and voice AI is ready to drive ROI, and it's at an inflection point. I spent about 9 years working at Tavant AI, building foundational language models, which were at the heart of the automatic speech recognition or speech-to-text models. And that was very core to the voice AI. Voice AI product, if we kind of break it down into units, you have the automatic speech recognition. You want to convert the voice into text. And the text earlier used to be fed into a dialogue management system, which was like based on state machines. And then you would get a response, which you kind of convert from text to speech. So that was kind of the typical workflow. And with the advent of large language models, you've gone from using a state machine to using the LLMs to handle the dialogues and the state. At the same time, there have also been advancements on the ASR side, automatic speech recognition side, and also on the TTS side, the text-to-speech side. So I'm going to draw on my experience of working in building the voice AI and working across the stack, and then also looking at it from the perspective of a vertical SaaS company, which has very successful product, and then how can you leverage voice to drive some of these product features. It could be things like voice agent. Can a voice agent interact with a customer and achieve certain tasks? And if you want to have a field service assistant, you have a technician in the field, and you have certain set of questions, can a voice agent reliably answer those questions? Or it could be things like customer support bots. I think voice AI has evolved significantly, and it's taking on more and more complex tasks and is become more reliable. And now I think is at an inflection point. And when you think about voice AI in enterprise, you can think of use cases like a voice agent. If you have a voice agent that can, say, take calls after hours, and it can answer basic questions like, hey, do you operate in my area? Do you offer these type of services? If you do, what's your availability? And you negotiate availability, and maybe you can even make an appointment. You can also answer questions about your product based on, say, a knowledge base, and then you can answer questions about the product. And why voice AI is at an inflection point now? One, I think the advancements in the ASR, the speech to text. Earlier, the accuracy or the standard in the field is to talk about word error rate. If you utter 100 words, out of 100 words, how many do you actually recognize correctly? Humans are around 97% accuracy or 3% word error rate, but we recover very reliably. You might not register every single word the other person is saying, especially in a conversation, but you can understand what they're saying and you can respond effectively. And the models went from having 6, 7, 8% word error rate to now less than 3, 4% word error rate, depending on which benchmark you're using. And there are various aspects of these benchmarks. You might be measuring it in a noisy condition. You might be measuring it with a clean auditory setting. And that space has moved significantly, and the word error rates are much, much lower now. And if you kind of take a benchmark like Libre Speech, it's around 3 to 4% word error rate. And two, the large language models have essentially replaced the dialogue management, where earlier you would have to keep very specific set of contexts. You understand what they're asking. Is it about the location? Is it about what service you have provided previously? So there was limits on the type of context you could keep, and then the state machine that you could operate with. Now with large language models, you can have really large, long contexts. So that space has evolved quite a bit. And on the text-to-speech side of things, the speech has become a lot more natural. It's become so natural that you have to introduce artificial errors. Like you have to introduce pauses, filler words, ums, ahs, and then you also have to pause just so your TTS sounds natural. And you feel like you're interacting with a person. And that is driving the adoption of voice AI. And there are challenges with voice AI. And I think what really helped me is drawing on my experience of voice AI's tech stack and looking at the applications where I was trying to build it and really understanding what are the key challenges to address. One key aspect is latency. Typically, when you have two people talking, between turns, you want to be around 200 to 300 milliseconds. And if it's anything above 1 second, you perceive as a delay, and you immediately know you are interacting with the system. Earlier, say even 3-4 years ago, that turn-by-turn latency used to be 2 to 3 seconds, which is quite a long time. Now you can bring it down to like under a second, which is acceptable. And that's one of the key drivers. So if you kind of start looking at some of the use cases and what kind of metrics we can drive, if you have voice agent, and you might have a preference to say, hey, I don't want the agent to do a booking. All I want it to do is take notes and send a summary to an agent. Somebody's going to look at it later. Or you might have very specific set of questions you want to answer, and you are like, hey, this is my threshold. These are the types of questions I want it to answer. You can also say, hey, don't answer any questions about pricing, for example. And that brings us to some of the challenges, which is you want context adherence, which is kind of a way of looking at hallucinations and what kind of hallucinations happen and how do you kind of limit those types of hallucinations. So you want your LLM response to honor the instruction that you have provided. And there are very simpler use cases or low-risk use cases. Like, hey, I want to handle calls after hours. That would have become missed calls or abandoned calls. Now, I can generate leads, or I can even generate revenue by booking the call. So you essentially can reduce abandoned calls. You have more leads, which will lead to revenue. You can also look at things like what we call second chance lead, which is you got a call, interaction happened, it didn't lead to a booking. And you can go look at those calls and say, out of these calls, which are those calls, if you were to call back, could actually lead to a booking? So you can do that type of offline analysis, which is distinct from real-time use case. So you have offline use cases like you could be doing transcription, or you could be generating summary, where latency is not as much of a constraint. But when you have real-time interaction, latency is a key constraint. And you could have use cases like assist for field services. You have, say, a technician in the field, say they're replacing an AC, and they want to know what was the work that was done here before I got here, and what else do I need to know about the equipment here? Maybe the manufacturer doesn't make this equipment anymore, so you also know you probably are not going to get the same exact replacement parts. You might also want to ask questions about warranty. If, say, this assistant was not available, you had to call somebody senior in your office. If you could catch hold of them in time, they would respond to you. So you essentially made this technician a lot more productive, and they are a lot more autonomous. And this could be a lot more useful, especially if you have technicians who are onboarding or they're in training. And you could also have customer support, which say work really well as a chat. Now you put voice as an interface, and it's reliable, and it's a lot more easier to interact with. So the other aspect to think about is, as voice AI becomes more trustworthy and it becomes more reliable, we will resort to voice as our interface as opposed to typing. The reason why we type is because voice is not reliable. If voice is reliable, we'll just talk to our devices. And eventually, we'll probably get into cross-modal type of interfaces, to Manish's point earlier this morning, where you might have gestures and cross-modal input. But as of now, I think voice AI is going to be the primary interface to interact with AI. And there are consumer applications. So some of the work that we did at SoundHound was to enable voice AI in automotive. You could have, sometimes you don't have connection. You might be in a remote place, but you can still interact with the car and ask it to operate on the climate control, or increase the volume. So all of these use cases can be driven off of edge compute that you have on the car. And one of the other reasons why voice AI is at an inflection point is because you can run many of these inferences on edge compute. And as devices, the compute in these devices become more powerful, and the types of models that you need, you can distill them down to have fewer parameters, you can quantize them, and as your inference becomes cheaper, and then you have more powerful compute in your edge devices, then you can drive more use cases. You can already have use cases like drive-thrus, where it's a very complex environment. If you kind of think about rolling down your window and you're talking across a distance, and there's a lot of noise, a lot of background noise, and you're asking to add some items, and you might change your mind. You want to remove something, and you want to add something else, and you might get the price, and then you're like, oh, are you ready? Okay, I'm ready. But by the way, somebody from the back seat says something, and then you want to add something else. So it's a challenging environment, both in terms of noise conditions. There might be accents that you might have to deal with. Then also, it's always on. There might be other conversations that are happening. You have to decide whether it's relevant or not to this particular context. So you have to handle all of these different use cases, and it works very reliably now. So the kind of under the hood, some of the things that we talked about, the word error rate, it continues to go down. And the other aspect that's happening with automatic speech recognition is we used to have acoustic model, a language model, and when you have an audio stream, you break the audio into audio frames, and each audio frame emits probability of a sound or a phoneme, and then you combine that information with the predictions for the words. Language model basically says what word comes next, and then you combine those two pieces of information to say, hey, what is the likely path of words that explains this audio the best? Whoever has the highest score, that's the sentence or the sequence of words that explains that audio. Now, folks are training end-to-end models, where you train one model to go all the way from raw audio to text, where you don't have these intermediate representations for phonemes. What that does is you will end up with one inference that you have to do, instead of having to do multiple inferences with LLMs and multiple inferences on the acoustic model. You'll have one set of inferences on one model, and you could have much smaller footprint, and it'll further reduce the compute. So if you have reduced compute, which means you can run more of these on edge devices with lower compute. And then text-to-speech sounds more natural, and you can have various voices. You can even, with very little fine-tuning, you could, with very few samples, you can make it sound like your own voice. And then the dialogue management system is more sophisticated because of the LLMs, and the latency is less than 1 second. So the other aspects that we can look at are real-time accent translation. So accent has many aspects. You could do accent translation while still retaining the identity. You could correct things like pronunciations while still making the voice sound like from the original speaker. Real-time emotion detection could be useful for a voice agent that's handling a call in a call center, where you detect certain emotions, then you might want to escalate to a human. And there's also noise cancellation. And this could be quite useful when you have, especially like babble noise. Babble noise is one of the hardest types of noises to deal with because you have multiple people talking. It's kind of like the, and you have to isolate which noise you have to pay attention to. And there is the real-time language translation, where you could have, say, you want to have a human agent respond, and that agent speaks, say, 2 languages. You could have, on the other side, a person speaking any language, and you could translate it to the languages that the agent speaks. And being able to do that in real time is the key. And that's why latency is very important. And this is all leading up to end-to-end systems being speech systems. You have voice, and the voice is the output. Contrast that with use cases like you want to do transcriptions, medical transcription. If you want to do domain-specific transcriptions, the challenge there is being able to deal with the complex vocabulary specific to that specific domain. But then you have the luxury of time. You're not trying to do this in real time. You're doing it offline. You can do one pass, rough pass, then you can do a second pass. You are more focused on accuracy, or you have like a Zoom call. You want to create a summary of that. You have the luxury of time. You're not trying to do this in real time. So you can achieve much higher accuracy. So the critical issues, we've kind of realized this, especially for real-time use cases, is latency. The goal is to be closer to 200, 300 milliseconds, but even under 1 second, it's good enough. So the other aspect is hallucination. Anytime you define an agent, you have constraints. I don't want to talk about certain things. So say pricing is something that you don't want to talk about. Or you probably don't want to talk about diagnosing the problem. Can you tell me what the problem is? No, you don't want the agent to kind of go into the aspects of speculating. So these are things that you can specify for your agent. You can say, hey, these are the instructions. I want you to adhere to it. So the challenge becomes you have real-time conversation. And in that real-time conversation, you have to come up with a response, but you also have to make sure that you're not hallucinating. You have to adhere to 2 things. One is you have to adhere to the context. This is the context. This is what you know. And if somebody says, if a place is open Monday through Friday, and if they say, hey, are you open over the weekend? If there's no information, you say, I don't know. Or if you know the information, you can talk about it. So that's the context adherence. You have that information in the context. The other one is the instruction adherence. You say, I I provide you this information, but I don't want you to specifically talk about these things. So that's the instruction adherence. And you have to do an inference on these things in real time. So before you respond, you have to look at the response that came back and say, hey, am I hallucinating? Am I adhering to the context? Am I adhering to the instruction? And then the next aspect is escalating to a human. If, for whatever reason, it could be like because of the emotion that you detected, or it could be because of them specifically asking, hey, I want to talk to a person. That could be a cue that you have to escalate to a human. So there could be any number of aspects for which you need to escalate to human, which you need to detect and say, hey, I can come out of the conversation and have to escalate to a human. So I think voice AI has come a long way, even just looking at it like past 2-3 years. And when you think about the interfaces to interact with AI, I constantly keep testing, like ChatGPT or any of these powerful LLMs. I want to interact with voice. A lot of times I run out of tokens, but it's not because the interaction isn't convenient. And you can also have them in always-on mode. You start a conversation, you probably have observed that earlier you had to say, hey Siri or hey Google, and you no longer have to do that if you're trying to interact with the ChatGPT's voice version. It's always on. You can ask a question. It knows whether you were talking to ChatGPT or there was some babble noise or background noise. It's able to make the distinction. And there are very powerful real-world applications where you are driving significant ROI. And I think till the next wave comes along with being able to effectively integrate visual cues with the voice, I think voice is going to be the primary interface for AI. Yeah.
Thank you, Kiran. All right, what questions might you have for Kiran? Please. Thanks, Bill.
Arguably, there you are. Again, arguably, Star Trek IV: The Voyage Home, one of the best movies in the world. You may remember that scene where Scotty picks up the mouse and talks to it, thinking the computer's going to talk back to him, right? And I appreciated your last slide, but we're not there yet, right? Like, the primary interface is still the keyboard. So do you have a view as to when, do I have to wait for the 23rd century? Like, when is that inflection point where the primary interface is going to be voice, in your view?
So let's kind of talk out loud and kind of think about this together. If I want to interact with my computer, my phone, I can actually use my voice to interact, right? So I don't have to type. And it's my typing errors and my dictation errors are pretty close to each other, right? And if you are talking about, hey, I walk into a room and I start interacting with devices around me, that's a separate set of complexities, right? So there are multiple devices. If they're all listening to voice at the same time, which one gets activated, which one responds, right? And that grounding and that intelligence needs to evolve, right? But if it's, hey, I know I'm interacting with this specific device, and it could be as simple as the proximity of the speaker, and then measuring the signal to noise ratio, and then you know which one needs to respond, right? As long as they're connected and you can interact with them. But if it is a matter of typing, so I used to type on ChatGPT. I don't type anymore. I just talk to it. And I talk to my phone while I'm driving, and I'm change the episode or go back to the previous episode. So if you look at it that way, there is no reason to type. The only reason why we used to type was because, at least for me, it wouldn't understand my accent. And I would say something and it would do something else, and then I had to go back and I was like, okay, I type again. And you do that repeatedly, and then our brain is going to compute the expected value, and it's going to say, hey, on average, you're having to type this instead of speaking to it. But because of how good the accuracies are, I don't think there is a need to type unless there are multiple devices. Then they all need to be connected and we can disambiguate.
So I would think, so I agree, right? I talk to my phone and everything. But the interesting thing, and I'm curious to your opinion about that, I love to read back what my phone presents to me, right? So I feel my typing is way slower than my speech, but my reading is way faster than the computer can respond in voice. So the ideal interaction is I talk to the phone says, okay, I got it, boom, and presents back what it thinks in terms of text, and then I respond back to that. Is that your experience?
So I'll give you kind of a couple of examples. So I generate stories for my son, and I make it read back because I end up consuming too many tokens, and it says, okay, it complains, not because of technical limitations, but because of the, when I listen to podcasts, and I listen to them at faster speed, right? So on average, your typing input versus speaking is around 10x faster, right? I mean, you can speak 120, 130 words, or fewer number of words, like 40 words per minute you can type, right? But in terms of reading and listening, so it could be both. I mean, depending on the context, right? So you read things faster if you know the context and what the material is, right? I mean, even like when you're talking, if you know the topic, you don't have to register every single word, right? And you when you're talking to a person, you're like, in the middle of the thought, you're like, okay, I understand. You gesture, and they move on to the next thing. You kind of know what I'm talking about, and then so that whole thing becomes like, dot, right? So like I don't have to elaborate on that. That's basically how we kind of process information, right? So when you're scanning, you kind of scan, and then you're like, oh, okay, I understand this paragraph, and you kind of move on to the next one, and you kind of summarize it, right? So, but if it's brand new topic, right? So then there might be equivalent. Yeah.
Let's see. There was a question or comment. I think I met.
I had a question. When you're training the voice model, is it the same as you could be training, for example, a generative AI where you're doing the typing and you're teaching it? Is it interchangeable? Are you training it the same way, or does the voice AI have to take a different path with respect to how quickly it needs to respond to you?
Yeah, so that's a great question. So if you kind of think about just the ASR part, right? So the automatic speech recognition, speech to text part. The goal for that, the language model in that context, is to disambiguate between sequences of phonemes that are similar to each other. For example, I say ice cream. So ice cream as in ice, the word ice, and then cream. That's like, something we want to eat. And then there's the word I, like the letter I, and scream, right? Like screaming. So both are phonetically equivalent, right? And the goal for the language model in that context is to disambiguate between these two. And I want to know that, if I say I am eating ice cream, and that's the sequence of words, that's more likely than saying, I and scream, right? And that's the job of language model in that context, to disambiguate between phonetic sequences that are, equivalent, right? And you don't need, like, say, $100 billion parameter language model to disambiguate that. And that's based on the phonetic context of each language, right? So like each language might have different types of ambiguities, so you just want to resolve that. And then the language model itself, the large language models, the goal is to try and represent all the information as efficiently as possible, right? So you want to learn about all the possible sequences, and you want to learn different words and different phrases are equivalent, and the goal being eventually when you respond to a question, you want to be able to answer it. So to kind of answer your question, the language model that you need for the ASR itself can be much smaller. And that's part of the reason why there have been models like CTC, where you can predict the letters sequences directly, and then also end-to-end models where you don't have to have an acoustic model and a language model, and you just train one model.
Thank you.
Okay. Thank you so much, Kiran.
Yeah.
How about another thank you for Kiran?